and it's my pleasure to welcome you all here today for AFOSR's 60th Anniversary Speaker Series. Since October, we've hosted 10 of these series on a variety of technical topics. It's been a wonderful and outstanding diverse group of speakers outlining the importance of AFOSR's basic research contributions throughout the years. The speakers have also forged allowed a wonderful way to forge stronger alliances with AFRL, and we're streaming today, and we're looking forward to the interaction that can come from that. Today, we have Professor Edl Schamiloglu. We round out this series with you as the world's leading expert in high-powered sources of coherent electromagnetic radiation. You hail from the University of New Mexico, where Edl is the director of pulse power beams and microwave laboratories. His areas of research include physics and technology of charged particle beams, pulse power, propagation of high-powered electromagnetic radiation, and high-powered electromagnetic effects. He's the associate editor of the Journal of Electromagnetic Waves and Applications, a fellow of the IEEE, member of the IEEE Nuclear and Plasma Pulse Power Society, and a member of the American Physical Society, and a member of the Cornell Society of Engineers. Yes. One other thing about Edl, he has one fault. He's a terrible Yankees fan. So we all have to put up with that today. But beyond that, please join me in welcoming Edl for our talk today.
Thank you, John. And I'd like to thank Dr. Russell for the invitation to present. I'd like to congratulate AFOSR on the occasion of your 60th anniversary. I think the seminar series is a wonderful idea of sort of getting to the trenches and plucking out people to present, and I'm honored to be part of this celebration. So my presentation is entitled Directed Energy Microwave Research, Virtual Prototyping and the Paradigm Shift. It's sort of autobiographical in nature. I've been working in this field for 25 years, and the presentation sort of follows the path and the trajectory that my research program has taken during that time as well. So we're celebrating over 40 years of research in the design of sources of high-power electromagnetic radiation. The birth of this area was in the late 1960s. It has two lines of genesis, one in the US, one in the Soviet Union. And the initial decades was a decade that we call the Power Derby, where you would go to an international conference one year, and scientists in the US would say, we generated this much power. Next year, the Soviet colleagues would say we generated this much power. And that continued for about 20 years. Then, in the 1990s, the phenomenon that was given the name pulse shortening emerged and reared its ugly head. So what happened was the power derby quickly came to a stop, and the once possible goals of achieving very high powers for very long periods of time was not to be had. At the same time, virtual prototyping came to the table, and using sophisticated particle and cell codes that really allowed the computationalists to take the lead in designing sources. So we are now entering a new generation, sort of the third generation of HPM source research, where the devices will be effects-driven. So here's my outline. I'll give an introduction to high-power microwaves. I'll explain the history of the first 20 years where experimentalists were king, and they led the way. Then the paradigm shift occurred where the experimentalists played the role of validating simulations. And now we're entering a new period of time where we are smarter, more agile, and our sources are developed based on their ability to perform certain effects. So I have three preambles. One preamble is a quote from a book that Dr. Barker and I had edited in 2001. And basically, U.S. Air Force General Hap Arnold proclaimed that the first essential of air power is preeminence in research. I think this was correct in 1944, and it's correct today. Second preamble is, I think the AFOSR and the DoD in general are interested in directed energy microwaves for these reasons, among others. First of all, microwaves propagate at the speed of light and present an all-weather attack of enemy electronics. You can cover multiple targets with minimal prior information on the characteristics of the targets. You can perform surgical strikes at selected levels of combat. There could be minimal collateral damage in politically sensitive environments. Simplified pointing and tracking compared to other technologies. And potentially deep magazines, meaning you can operate for a fairly long period of time without replenishment. So my third preamble is that the US Air Force has taken the lead in the development of directed energy, including high-power microwaves. And in fact, the Air Force has been designated the lead service for directed energy. And as a footnote, the Air Force Weapons Lab, which is now Kirtland, Air Force Research Lab, RD at Kirtland in particular, began its research into sources of high-power microwaves in the late 1970s. And I arrived at UNM in the late 1980s, and that's when my program first got its jump start by sponsorship from AFOSR, namely Dr. Barker. All right, so let's go into the introduction. So high-power microwaves is a fairly imprecise term. It usually denotes sources of coherent radiation that span the frequency range nominally of 1 gigahertz to 100 gigahertz. However, today you can even consider terahertz radiation as high power. And what the PF squared scaling means is that 1 gigawatt, so 1 billion watts of microwaves at 1 gigahertz, if you were to follow this power times frequency square scaling, says that at terahertz, roughly 1 kilowatt would represent high power. So solid state and other sources of terahertz tend to be fairly low power in the milliwatts. It is certainly possible that beam-driven sources will be achieving kilowatt power levels fairly soon. But the bottom line is most of the HPM sources I will describe connote the use of pulse power to generate electron beams, although as I acknowledge here, there are other sources available, but I will not discuss them. So pulse power is also an imprecise term. It typically means the compression in time of energy. So one would take energy and store it or accumulate it over a fairly long period of time. An example of that would be charging capacitors over a time scale of many seconds. And then through clever switching techniques, releasing that energy over a short period of time. So let's say nanoseconds to microseconds. Since power is energy divided by time, this tells you for a fixed energy, you can achieve high instantaneous peak power levels. And so pulse power is, in fact, the technology that we use to generate high perviance electron beams that drive narrowband high-power microwave sources. Now, I have a plot here that plots peak power versus average power. And the peak power here goes up to 10 gigawatts. It might even go higher. So all of you most likely have a microwave oven at home. Your microwave oven at home is roughly on the order of 1 kilowatt, which is 1,000 watts. So that's sort of in this region here. The energy in your microwave oven is a lot compared to the energy that our HPM sources deliver. As an example, if you take a mug of water and if you heat it for 5 minutes in your microwave oven, that's a lot of joules of energy. That's many, many thousand joules. The joules in our single microwave pulse is typically 100 joules or less. So we have high peak power levels, but we have very little energy in our pulses. And it turns out that the history of high-power microwave sources is intimately linked to the history of the development of pulse power. So modern pulse power was attributed to Charlie Martin and his colleagues at AWE, which is the Atomic Weapons Research Establishment in the UK. So Charlie was actually charged with building sources to radiograph dynamic implosions. So nuclear weapons, they wanted to understand how the explosives that initiate the nuclear reactions, how they penetrate through all the mass internally. And commercial sources of X-rays were insufficient. They did not have the appropriate fluence to be able to image those dynamic implosions. So Charlie went off on a tangent and started building capacitor banks, Bloom lines, transmission lines, parallel plate transmission lines, because he wanted to generate not only high voltage, which is what you need to generate X-rays, but at the same time, he needed to generate high currents. So existing current sources at high energy might have had currents on the order of 1 ampere. Charlie paved the way of generating sources that generate high voltages, but at many amperes. So pulse power sources were developed at AWE, and it turns out that there were some faculty at Cornell who, as students, spent some time at AWE and brought that technology back to Cornell. That technology also came to NRL, Naval Research Labs, and to Sandia National Labs. And then a couple of plasma physicists at Cornell, it was John Nation, who recognized that the ability to generate not only high voltage beams, but high voltage beams with high currents can allow you to do interesting things. So then the light bulb went off in their heads, and they said, oh, let's think about all these classical microwave tubes. As an example, you have the backward wave oscillator, which was developed in the 1930s and 40s. And he said, wow, if I can put an electron beam that had a megavolt of energy, and instead of 1 ampere of current, it had 10 kiloamperes of current, he quickly did the math, and he said, oh, that's 10 gigawatts of beam power, and if I can only do that with 10% efficiency, that gives me 1 gigawatt. So this technology basically took the classical microwave tube technology and allowed it to be extrapolated to achieve super high power levels. And at the same time that John Nation and others in NRL and the Army labs were doing that here, there were a group in the Soviet Union at the Institute of Applied Physics in Gorky, which is now Nizhny Novgorod, as well as in Moscow, that were sort of beginning their studies. So you can see here the historical development of HPM. Again, this is the PF squared scaling I mentioned earlier. This is decades. And notice the classical microwave tube world is down here with powers saturating. And then with the birth of pulse power, you have the high power microwave sources that have been developing over the decades. So you can see here there's a new lineage, a new genetic line of codes. And I have to point out here that many people don't realize this, but the success of Silicon Valley occurred undoubtedly because of the infrastructure that was in place in the Bay Area in Palo Alto by the microwave tube industry. In other words, it was Stanford became a great university because the Varian brothers and other corporate executives in the tube industry wanted Stanford to become great and gave them money, gave them equipment, and that's what led to the follow-on successes with the Silicon Valley. So as I mentioned, it turns out that's a bunch of plasma physicists that are leading the charge in HPM source research. That is my background, that's John Lugenfland's background, that's Bob Barker's background, as John Nation and Michael Patelin. The reason is the difference between the high power sources and the conventional tubes is that the conventional tubes have fairly small currents. So if you were an electrical engineer in the late 1950s studying undergraduate electrical engineering, you learned about all those things. You learned about vacuum diodes, you learned about microwave devices, because that drove the core curriculum. And it was the electrical engineers that worked on those tubes. Now the reason is because the current in those tubes were quite small, so you could ignore to first order the self fields associated with them. So for all practical purposes, you can use single particle theory, F equals ma, to describe the electrons, and then combine that with circuit theory and Maxwell's equations. You can describe and design tubes. Not so with high power microwave sources. With our high power microwave sources, the current densities are so high, the currents are so high that the self fields become so high that single particle theory is inadequate to explain the propagation of these beams. You need to have a collective theory or a kinetic theory, and in fact, that's what plasma physicists are good at. They understand the interaction of self-fields and space charge and fields. So very quickly, so the requirement then for pulse power is the following. In the ideal world, you'd like to have a voltage source, a voltage waveform to drive your electron gun that looks sort of like this. You would like it to be rectangular. You would like the rise time to be as short as possible. You'd like the amplitude to be many hundreds of kilovolts, maybe megavolt. You would like the pulse to be absolutely flat, which means constant energy for tens to hundreds of nanoseconds. And that's sort of hard to do. The reason you want that is because beam-driven sources inherently operate because of some synchronism condition between electron energy and phase velocity of electromagnetic waves. So if the phase velocity of electromagnetic waves stays approximately fixed and is determined by the structure, then you'd like to have a fixed electron energy to interact with it. That's why you'd like to do that. And that's fairly hard to do. This is not something that someone can do in their garage. And then an overall system would look like this. You have some prime energy in the laboratory. It would be your wall plug. On a mobile platform, it might be batteries. Batteries charge capacitors. Then switching it, you have pulsed power. So again, the area under this curve should be the same as the area under that curve, except that we're compressing this in time. That gives us the high voltage. The high voltage is applied to an electron gun. That generates an electron beam. The electron beam propagates through some RF interaction region, and there's a resonant interaction. You take energy away from electrons, you grow RF, and that's nature. We had nothing to do with that. Nature determines that the instability is such that you remove energy from electrons and you grow microwaves. And then you radiate it, and if your application is electronic attack, then presumably something will happen to some electronics. So one slide on the fundamentals of HPM generation. Basically, electrons radiate because they are accelerated in some periodic fashion. And by acceleration, we mean it's really a change in momentum. The radiation could be coherent or incoherent, and the contributions from electrons would tend to reinforce the original radiation to give you the proper bunching. And if you have a coherent interaction, which is what we want, then if you have n electrons, the power will go as n squared. And finally, one thing to take away from this is vacuum devices are inherently more efficient than solid-state devices since the electrons are free electrons. The efficiency, for example, in a commercial oven magnetron can reach as high as about 90% efficiency. That is the efficiency in converting beam energy to electromagnetic energy. And no solid-state device can come anywhere close because electrons are not free in solid-state devices. They have to flow through matter, a lot of interactions and scattering going on. So free electrons are good electrons. All right, so then we enter the period of time, the 1970s through early 90s, where the experimentalists were leading the way. What I mean by that is our computational friends back in those days were only beginning to develop tools. We had some theoretical guidance on design of sources, but really the experimentalists would build sources, which is fairly expensive, take their measurements, and then the theoreticians and computations would try and match the results. That was the world back then. So that led to the HPM Power Derby. So here are some representative sources. This is from the Institute of High Current Electronics in Tomsk, Russia. I've visited this facility several times, and this particular device is still there, although has not changed in probably 20 years. And that's the gamma accelerator. And this was used to generate 15 gigawatts of microwaves. So here, typically, you have the output horn antenna. This is the solenoidal magnetic field. And really, the area where you take energy away from electrons and grow microwaves is inside this device, and it's about the size of a pint of beer. Okay? And all of this monstrosity behind it is just the pulse power to generate the electron beam. Here's the same accelerator looking further back, and that's the canonical size of a Russian scientist. This is the Orion HPM facility, which used to be in the UK. So this was built by Physics International. At the time, it was a state-of-the-art, not portable, but transportable HPM source used on test ranges. You have several of these trailers, and this particular source that this guy drove would be a bunch of different magnetrons to generate anywhere from high hundreds of megahertz to a few gigahertz radiation. And here are some photos of HPM sources from AFRL in the mid-90s. The magnetically insulated line oscillator, MILO, was very hot during that period of time. Scientists at AFRL really liked the MILO because one advantage it had is it did not require an external magnetic field. So that saves system efficiency and portability. Here's a relativistic Kleiston oscillator, and here's an old gyrobiro. And just to orient your scale, these are about 1 meter this dimension, 1 meter this dimension. So these are fairly big devices. And this is our PI-110 at the University of New Mexico that we use to drive backward wave oscillator. And of course, you saw the sizes of the pulse power generators. Really, what the community needs is more compact sources. If we can take the output of those huge devices and make them smaller, it would really benefit the community. And of course, during this period of time, we had numerous university programs that were launched in FY94. Dr. Barker was the program manager on, I don't know if there ever was another trinity of MURIs. It was one MURI cycle with one program manager and 3 separate MURI grants. And these were an amazing period of time. So I was aligned with the Texas Tech University led by Chris Christensen. I was sort of the low man on the totem pole back then, just sort of getting started. And then we had the West Coast team led by Neville Luman, and then we had the East Coast team led by Vic Granitstein with John Nation. And I want to point out that many of the students who received their PhD during this period became leaders in the field, and one example is John Lugensland. John Lugensland was a PhD student whom I first met right around this time at Michigan, and he was working heavily on his dissertation research. And so the point to take away is these programs are not only good because of generating all the knowledge and the transitions to the labs, but also educating graduate students who then do great things themselves. So you have a bunch of experimentalists in the US and the Soviet Union leading the charge, everyone coming up with new ways of spending money and building new devices that would convince leaders that they can generate more power and more efficiency. But then the experimentalists ran into pulse shortening. So this is a quote from a book in 1992 by Jim Benford and John Swagel called High Power Microwaves. I co-authored the second edition of this book, which came out in 2007. So here's a quote back then. So back then in 1991, they predicted that HPM power levels of 10 to 100 gigawatts and radiated energies of 10 kilojoules and greater were to be achieved by now. And by now, they meant by the 2000s. So clearly, something went awry because you had all these source developers and source researchers being very optimistic that they're going to keep going and keep generating greater and greater power with longer and longer pulses so that you can have higher and higher energies. But then all of that basically came to a crunch. So AFOSR at this time sponsored an international workshop through EOARD at Edinburgh. It was the pulse shortening workshop. So program managers at AFOSR got together and thought it would be a good time to bring the world together. And so we had scientists from all over the world, from that's Kyle from New Mexico, AFRL, but also we had many scientists from Russia and all over. And it was a very useful period of time. And then the whole bunch of scientists left this workshop and went back to their labs. Some of the Russian scientists received EOARD funding. And there was a lot of synergy at that time, a lot of discussion, a lot of working well together to try and tackle this problem. So what went wrong? Well, pulse shortening ultimately was determined to limit radiated HPM to about 100 nanoseconds, although some devices can go beyond that. But As a general order of magnitude, about 100 nanoseconds. So why is that? And the short answer is ultimately some unwanted plasma evolves in these devices. And 100 nanoseconds is approximately the time it takes for a plasma ion to move far enough that it does something. And in my case, we were studying pulse shortening in backward wave oscillators. And all oscillators have start conditions. It takes some initial current to get the oscillation going. And using laser interferometry, we measured the evolution of plasma along our backward wave oscillator walls, and we learned that the coupling between the beam and the slow wave structure decreases. So whereas early in the pulse, our beam current is above the start current and we generate microwaves, after the plasma evolution, the start current becomes higher. And then, therefore, the beam current, which is still the same beam current we had in the beginning, is no longer above the start current, and the oscillations terminate. And that was a big problem. So everyone had to recalibrate and rethink. So the idea is, we need to move away from the flamethrower mentality. In other words, stop this nonsense with generating 10 gigawatts, 100 gigawatts. Let's move away from that, and let's be a little bit more smarter. And some people were saying, well, maybe the powers that we're generating is good enough. Maybe a gigawatt is good enough. But maybe we should do a gigawatt, but instead of having an oscillator that only fires once because of the pulse power technology, maybe we should have a higher repetition rate. So that's one avenue of inquiry that developed. And then we need to be smarter. Maybe instead of developing an oscillator that just has a flamethrower and generates a lot of power, it might be the case that if we modulate or temporally shape the waveforms, then maybe we can achieve an end result more efficiently. And we need to maybe go away from oscillators and move to amplifiers to achieve this. But in the end, you need advances in compact pulse power so that these can leave the laboratory and help the Air Force achieve its mission. So after that, in 2001, Dr. Barker led another MURI. This time it was two teams awarded for 1 year. One was led by the University of New Mexico and included Old Dominion and Nevada Reno. And another team was led by USC. And again, many of the students who received their PhD during this became leaders in DoD laboratories. I can list names of former students who are at Dahlgren, who are at NRL, and who are at AFRL. So pulse shortening occurred. At the same time, the paradigm shift occurred. And this paradigm shift occurred in the early to mid-90s. So prior to the early to mid-90s, the experimentalists were king, as I said. They tinkered, and modeling and simulation always played catch-up, trying to explain the experimental results. And absolute agreement, namely relative agreement, might have been okay, but absolute agreement was poor. Of course, today, it's a different world. Absolutely no metal will be cut unless the simulation demonstrates some unique and superior capability. I mean, it may not seem like that big a deal, but this really is a big deal. I mean, the ability to now virtually prototype on the computer to such a fidelity that you can pretty much be sure that if you build it, it will behave as simulated, that's astonishing compared to the way it was before. And the real reason is it's these developments of these particle and cell codes. So particle and cell codes are three-dimensional, fully electromagnetic, finite difference time domain codes that self-consistently solve the relativistic kinematics in a gridded environment of the source. And there are many codes out there right now. I would say probably IcePick, developed by AFRL, is probably the state-of-the-art in PIC, although there are many, many new codes emerging right now. So in my case, at my university, we were involved in a collaboration with AFRL and Sandia Labs that led to our understanding of why the PIC codes were failing. So this is our backward wave oscillator. This is an old article, so therefore I apologize. The quality isn't that good. But so we have an accelerator that we use to generate an electron beam. So this is Z in this way. This is R in that way. These X's represent a solenoid that generates an axial magnetic field. You have an annular or a tubular electron beam that's launched from this emitter. The axial magnetic field confines the beam. As the beam propagates across this waveguide that has a periodic ripple in the boundary condition, that periodic ripple in the boundary condition slows down the phase velocity of electromagnetic waves. Electromagnetic waves in a waveguide are all fast wave, meaning their phase velocity is greater than c. If you put a periodic ripple on the boundary condition through Fouquet's theorem, which is electromagnetic version of Bloch's theorem, the phase velocity decreases such that it's below c. So now you can have a relativistic electron be resonant with a phase velocity that's less than c, and you grow microwaves. So we were doing simulations using a code that was a precursor to MAGIC. It's called 2QUIC. It was being run at Sandia National Labs. And when we first were doing these simulations, we used to get terrible agreement between our experimental data and the simulation. So we decided with Ray Lemke at the time that we were going to sit down and we're going to figure this out because it seemed ridiculous that we were having so much difficulty. And the key turned out to be a discussion we had with Brendan Godfrey. Brendan was the former director of AFOSR. In an earlier life, he was a plasma physicist who did science. And he wrote a paper in 1974 at the Numerical Simulation of Plasmas conference in Evanston, Illinois, where it turns out that Brendan had created the algorithm that damped numerical noise. When you do a finite difference time domain scheme, you discretize the problem. And because you're running the simulations for many nanoseconds, the development of finite errors in the differencing scheme build up, and that's referred to as grid noise. And the way it's eliminated in simulations is they put in an artificial exponential damping factor. And it turns out that scientists at Sandia using this particular code were always studying low frequency phenomena, frequencies in the megahertz, maybe up to 100 megahertz. We were studying phenomena at 10 gigahertz. So we postulated what was happening is that the attenuation of the grid noise was actually also damping the radiation that was being produced in this device. So we performed a baseline set of very vanilla experiments. We performed concomitant simulations of those using the PIC code, and we decreased the attenuation coefficient until the power in the simulations and the power in experiments were in agreement. And after that, we no longer touched it, and then we started doing, instead of vanilla simulations, we started doing crazy simulations. So one example of a crazy simulation is we took the slow wave structure and through very small increments, sub-wavelength increments, we started displacing the slow wave structure to the right. So you left a gap between the electron gun and the slow wave structure. And we had reasons for doing that, which I don't have time to get into. So we gave this to Ray as an exercise. He went ahead and did his simulations, and we came back, and then we were astonished because the simulation results and the experimental results were dead on. So one thing we noticed is the efficiency of the device, and by efficiency I mean microwave power divided by beam power, as a function of how much space you introduce. So the more you go to the right here, the larger is the gap that you're introducing. And the triangles, well, I can't tell from here, but we have triangles and squares, and one of them is simulation, one of them is experiment. Experiment is an average, where each point is an average of at least 10 data shots. And you can see here a very, very good agreement. And also, we noticed that the RF frequency also changed because of the introduction of that gap. And again, the predicted, simulated, and experimental results were in excellent agreement. So this was one of the first times that a PIC code and experiment were in good absolute agreement without any post-simulation explanation or, oh, that's where that figure went. I was wondering what happened to it. So 20 years ago, AFRL, under the leadership of Bob Peterkin, I believe, launched an effort to develop IcePic. So IcePic stands for Improved Concurrent Electromagnetic Particle in Cell. All of these codes have features that are common to them. All of these codes self-consistently solve Maxwell's equations. They use a discretization. Sometimes that's done automatically. Sometimes that's done manually. They have a scheme this is sort of the update representation on how in one simulation time, how values of fields and particle quantities are updated to the next time step and so on and so forth. I don't have time to get into the details. So all of these PIC codes have all of this pretty much in common. What's different is some PIC codes can handle cylindrical geometry. Others perform 3D simulations using only Cartesian grids. Some PIC codes use explicit methods for solving Maxwell's equations. Some use implicit methods. So there are some nuances and some differences between the codes, but the main algorithms are quite the same. So there are numerous PIC codes out there. As I said, probably IcePic is the leader in the community, but you also have MAGIC that we use and is pervasive in US universities. Simon Cook is working on a code called Neptune. One big difference with IcePic is that from the start, 20 years ago, it was developed as a fully parallelized code. So typically this runs on 64 processors, and it has a great way of doing load balancing, where if one processor isn't working too hard, it's able to shift and more evenly distribute the load on each of the processors. And there are commercial codes. CST, which had Microwave Studio, recently launched Particle Studio, and although it does well with some devices, it doesn't do well with other devices. So to give you a feeling, this is IcePic looking at a commercial magnetron, 100 kilowatt magnetron. It gives you, this is called a visual fly-through. This allows you to rotate and look at the movie of the geometry. It's not operating here. This is fully static. It's just showing the device. And the red represented the thermionic cathode. It's a helical cathode. So this is a run now where we're not showing the particles because it would be too noisy. OK, so those are the fields oscillating in and out of the cavities. So the great thing with these codes is that you're able to put diagnostics pretty much anywhere you want, whereas in the experiment, you're limited with your ability to put diagnostics because you will have breakdown problems, you have high electric field environments. But in a code, you can put diagnostics anywhere, so you can really understand the physics of what's going on. So what we've been working on recently at the University of New Mexico since, for the last 7-8 years is studying relativistic magnetrons. The particular geometry we picked was called the A6 magnetron. There's nothing particularly special about it. It's A because it's the first magnetron, 6 because it's 6 vanes. It was developed by the late George Beckefee at MIT. And the reason we picked this device is because it's the most studied relativistic magnetron in the literature. So this is something that we manufactured at the University of New Mexico. It's about the size of a Coke can. And the electron beam in this device is emitted from a cathode, which is in the center of the device, and then electrons E cross B drift around the azimuth of the device. So as an example, something that we came up with a few years ago is called the transparent cathode. So typically, the electron gun in this device would be this cylindrical cathode, which nominally would sit in the center of this device. And typically, graphite is used because it has the ability to produce a surface plasma at 100 kilovolts per centimeter. And from that surface plasma, we're able to extract free electrons. And we were concerned with my colleague, Michael Fuchs at UNM, that our short pulse accelerator would be insufficient to have this magnetron operate because our accelerator is only about 15 nanoseconds. And magnetrons notoriously take a long time to kick in and build up the oscillation. So we were thinking of ways to decrease the time it takes for oscillations to begin. So we came up with this based on the following idea. So this is a plot of E theta. E theta is just the microwave first order RF electric field inside the magnetron. This is E theta as a function of radius. So the anode radius here would correspond to, this surface here. That's the anode radius. And then the cathode radius would be the surface here. So if I had a solid cathode, E theta will have to go to 0 at the surface of the solid cathode to satisfy continuity of tangential E. And we realized that if we drilled a hole down this cathode and then machined these slots this still allows the electrons to be born on the surface of the cathode, and at the same time, it allows the first-order wave electric field, instead of going to 0 on the surface of the cathode, it penetrates it, hence the name transparent cathode, and it goes to 0 on axis. As a result, where electrons are born on the surface of the cathode, you now have much higher electric field than you would normally. And we used magic to simulate this. So we're comparing 3 technologies here. One is the solid cathode. Another is a technology invented at Michigan called cathode priming. With cathode priming, they also take a solid cathode, except what they do is they allow electrons to be born in 6 discrete regions around the azimuth. And so our transparent cathode was invented at about the same time and independently of the Michigan work, and where we actually have 6 individual emitters. And you can see here, as you go across, it's all a snapshot in the same time. So this is 3.8 nanoseconds, 4.4, 5.9. So you see here the transparent cathode-driven magnetron comes up to a beautiful spoke formation and equilibrium flow in about 5.9 nanoseconds. Cathode priming takes a little bit longer, and then the solid cathode took a long time. So we've decreased the start it takes to oscillate from about 20 nanoseconds down to about 6 nanoseconds just by changing the cathode. And then we did the experiment. This is our CNIS accelerator at the University of New Mexico, and this is a pair of Helmholtz coils that our students made. The Coke can magnetron sits in the center here, and this is basically an antenna, and we have directional couplers on the other side. But as predicted, we did the experiment. You can see with the transparent cathode, we generate 10 times the power compared to the solid cathode. And I didn't mention this earlier, but the A6 magnetron is notorious for mode competition. And with the transparent cathode, we were able to eliminate mode competition by proper orientation of the cathode and proper selection of the magnetic field. So our degrees of freedom in operating this device is much greater than what you would have with a solid cathode. So virtual prototyping works. Hours of computer simulation guided us towards what direction we need to go in the experiments. And then we did the experiments, and we validated the code. So this basically shows the A6 magnetron. And this is what the simulation looks like. And what you'll see here are the electrons. And this is in looking at a cross-section. So here are the 6 emitters. Note that the electrons go in one direction, and the RF goes in the opposite direction. That's because this is a backward interaction. Electrons go one direction, waves go in another direction. And here, notice there's a four-fold symmetry. This is indicative of the 4 pi over 3 mode. And through simulations like this, where we're able to both study the plots and the fields, we're really able to make changes and adjustments in the geometry of the interaction space and optimize for greater efficiency, purer output, or whatever. So my final topic is sort of the 3rd generation. So the 1st generation in HPM source research, or the first period of time, was the power derby. The 2nd period of time was the sober realization of pulse shortening and stepping back and revisiting how we do things. That was concurrent with the development of virtual prototyping tools. And I think today we're entering a 3rd phase, or 3rd era, which can be referred to as effects-driven source research. And I go back here to an earlier slide that I showed, and I'm just highlighting what I mentioned earlier. Maybe what we need to do is focus on developing broadband HPM amplifiers, because maybe generating super high power and accepting, let's say a Gaussian waveform with the oscillation superimposed on it, maybe that's not the best thing if you're trying to use this to affect electronics. Maybe there are other ways of doing things. So the idea is you can maybe potentially make an interesting looking waveform at very low power, but then use an amplifier to just increase or amplify that amplitude to very high power. And I think that's sort of a new direction that the community is moving into. So effects driven, here is a sealed Pomona box that was, this is from work done at Maryland, where you can see damage to electronics. So yes, indeed, electronics are susceptible to intense fields. So that leads me to a new MURI that John Lugensland and Dr. Nachman are co-program managers with. We have one team, and we were just found out about this in May, and we have a team that's going to be working together to try and exploit metamaterials to perform dispersion engineering to maybe achieve beam wave interaction of interest to amplifiers that one cannot achieve using traditional materials. So we've got two groups that do HPM source research, myself and MIT. We've got a group from Ohio State that engineers metamaterials, and we have two applied mathematicians who will take our hands and lead us down the path on novel ideas for metamaterials. So here's our vision of where this thing is going. You know, we have our knowledge base among our team members. We have a technology base. We have integrated technologies that come from many facets of the DoD community, from defense and civilian radars to directed energy, communications, accelerated, and so forth. And we think that if we tie these communities together and put our heads together, we can maybe make some advances when it comes to HPM amplifiers. And an example of this is a calculation and a conceptual drawing from my colleague, Alex Figotin at UC Irvine. And he has come up with a way of achieving what he calls slow light. So the idea here is, how can you take the phase velocity of electromagnetic wave in a structure and take it down as low as you can go? And so that's going to be our jumping off point for going down the path in this new MURI. And here is an example of using degenerate band edge modes. The frozen modes, we believe, will allow for greater amplification of RF driven by electron beams compared to more traditional structures. So in conclusion, high-power microwave sources have been studied for over 40 years. AFOSR investment has supported the transition to virtual prototyping for more efficient and cost-effective source design. AFOSR investment has led the way to more compact sources of pulse power to drive such sources. And I think continued investment is paving the way to effects-driven source research, which will lead to novel amplifiers. And you know, we have a couple of, we have one book that came out with Dr. Barker on the source research, on the compact pulse power MURI. We had a special issue devoted to that subject. If you're more interested in this subject, there's the more recent book with Benford and Swagel, and I made sure we didn't do predictions in this version of the book. And finally, I'd like to thank Dr. Russell for the invitation to present this seminar. I thank my program managers for their continued support, and I would like to thank Tom Hussey as well for his support. And with that, any questions? Yes, Howard.
At the time when pulse shortening was being noticed, some of us who came from other fields were aghast at how dirty the vacuums were, how incompatible materials with vacuum were being used. How much did that contribute to the plasmas that were causing problems?
Okay, do I have to repeat the question? Okay, so the question was, at the time pulse shortening was occurring, many senior scientists were aghast as to how poor the vacuum conditions were, how crappy the materials were that we were using in these sources, and how much did that contribute? And I think the answer to that is a little bit. It contributed some. There has been work since then, both in Russia and in the US, where the tools and techniques of the vacuum tube industry were applied to making such devices. And in some cases, they did get some better performance, but it was not a huge increase. It was a subtle increase. And I think the reason is the vacuum tube industry uses those super great vacuums, great materials to achieve the clean, pristine conditions, but at the same time, they work very hard to maintain the field levels much, much lower so that they can operate these devices, CW. In our cases, you might use such materials, but the power levels that we have coming down these devices are still so huge that it comes back to bite you. So I think the answer is the reason why we use dirty materials and don't need great vacuums is because that's a very cost-effective way of achieving a result that meets the needs of the researcher or the mission. So I think it is doubtful that one will be able to practice all those techniques and achieve super high powers. You'll achieve 100 megawatts maybe, but getting to the gigawatt level, you will still have the problems.
Let me ask the follow-up question to that, and that is, there has been progress with cathodes, that aren't plasma sources, but are high current field emission cathodes, and there's been progress in essentially using better practices for better materials and better practices for processing them. So where do we stand? Are we going to get? How much have we improved, and are we going to improve any more?
So the question is, there have been some novel cathodes developed that, for example, have very little plasma compared to our more traditional cathodes, and some researchers have invoked good practices, and the question is, how much better can we get, and how much do we think things will improve? So to answer your question, I would say that the plasmaless or near plasmaless cathode emitters are great, and I think that the high vacuum techniques and materials are great, but they're being used more to facilitate rep rate operation as opposed to allowing these super high power sources to operate. So I think there's investment in that, but that's more to facilitate rep rate operation. I was told I do not have to repeat the question now. So.
Hi. I would say that materials are not crappy, but our understanding about the materials are crappy.
No, our materials are crappy. we put velvet inside these tubes. We do.
My question is on your ultimate aim to make these systems more compact. I am aware that the necessity of the supercapacitors or capacitor work, but in your virtual design and effect-driven approaches, what other systems or materials areas that you are really aiming for to make the system more small?
So
that's the reason I come to your talk, but I didn't hear that.
Is that the reason you came? I hope my answer won't disappoint you. So there are two issues here, okay, and they're separate. One issue is having higher energy density capacitors, understanding material properties better so that you can make drivers of high power microwave sources that are more compact. The actual HPM sources themselves, most of them are actually quite compact. And so when we're thinking about amplifiers and we're going down this path of trying to engineer dispersion relations that can help us do things that we can't do with ordinary materials, there we're not worrying so much about the size. There we're just trying to worry about the beam wave interaction, and so that's the piece that we're going to focus on. But if our colleagues and our future colleagues and collaborators can then help us make pulse power drivers that are a factor of 2 smaller than what they are today, then we can package them together and do amazing things. So those are 2 separate problems that are both important, but I think right now our focus will be on the electromagnetic interaction region, and we're not so worried about the size of the drivers for that.
To what extent has, or if any, superconductors been used either for coil windings or magnetron
Yes.
the gyrotons, and so on.
So superconducting coils are standard fare for gyrotrons, as an example. A gyrotron is a class of high-frequency source that uses a very high magnetic field and can operate continuously, CW. And so for them, it is critical that they have a cryomagnet, and that is a standard part of the source. Other sources, for the most part, do not require superconducting. In fact, in my work, in my lab, I have a PhD student who just came up with a permanent magnet design for our magnetron, which we seek to implement. So that's even better for us because a permanent magnet requires no liquid helium, requires no electricity. It adds weight, may add a little bit of volume, but from a system point of view is great in increasing the efficiency. So, but for some devices, yes, superconducting magnets are critical. For other devices, it's not as important.
Let's do Frederica and then Joe.
Do you want to just sit here and I can speak loudly, I think. Where do you see the modeling simulation evolving and which directions? For example, you talked about some of the codes and you talked about high speed that uses 64-way parameters. This is, old story, nearly 1,000 ways of parallelism. So how, first of all, in terms of the modeling simulation, where the directions are in exploiting sort of the higher computation capability?
Right, so the question was, where is modeling and simulation going? Virtual prototyping has now been around for 20 years. I may not be the best person to answer that question, but let me give you my take. So for the computation side of the house, I think the computationalists are now trying to take advantage of new hardwares that become available, like GPUs and so on and so forth. So you have a new generation of codes that depend on that. Analytically driven modeling is extremely complicated for these devices because of the nonlinearities and complexities. And there are some researchers who still are performing some analytics. There are some other tools that are available, computational tools that maybe don't require a full-blown PIC simulation, but maybe can do some more simple simulation that might be a 1D simulation, for example, studying electron energy and phase and getting an initial design for a code. But I think really when someone is serious about making something, they will do the PIC simulation before they purchase any metal.
A quick parenthetical comment is IcePic runs on 20,000 nodes for AFRL, and actually there's 100,000 versions being worked on.
So the emphasis will be to put more of the physics and
That's a good point, yes. So the I would say the direction that the community is heading in is basically making sure they get more of the physics and chemistry, right? Like surface models, ionization models, emission models, secondary emission models, getting the atomic physics and the chemistry to be high fidelity is, I think, the number one direction that the code folks are moving in. Yes.
So I think you partially answered my question, because I was going to ask specifically about, you have nice fidelity when you have nonlinear electromagnetic interactions with electrons, gap closure, pulse shortening. How good are the models at doing that? And I think these models are exactly what you need to be
right. So
the surface interactions.
I can't comment globally on that. I can just comment personally from our experience. Our experience is right now, for example, with linear beam devices, I think we have the important physics and the simulations are dead on. I mean, we had a project a few years ago where we were asked to design a frequency agile BWO for a customer, so to speak, at UNM, and we did it on the computer. We built it, and it was dead on. I mean, it was astonishing. I mean, I was impressed, and with the magnetron. But you try modeling a Vercator, virtual cathode oscillator, and it is awful. The modeling results aren't. And I think the reason is with a virtual cathode oscillator, you typically have grids or something, and you have electrons that constantly reflex back and forth. And there's a lot of surface physics and emission that goes on that the codes don't account for. And for that class of devices, that dominates, which is why the simulations are poor.
In the spirit of get the energy in slowly, get it out fast, I once got intrigued by frozen wave generators. is there any future for that or analogous devices where you switch them?
What's a frozen wave generator? I'm not familiar with those.
I think it's a Q switch.
Maybe
Oh.
that's why there's no future.
Oh, okay, I don't know.
I think of it as a Q switch accelerator concept.
Okay.
You drive up the source through with a high Q cavity and then break the Q.
Oh, so it's like a pulse compressor.
Correct.
Pulse compressor. There is active work. I even have a project with pulse compression, and the answer is to do something like that. Yes, that is a Walmart approach to if you need a gigahertz of radiation at, let's say, hundreds of megawatts, then the Walmart approach would be to do exactly that. You would accumulate energy at the desired frequency gradually in a high Q cavity. You break the symmetry and you compress the pulse, and you get amplification of factors of 20 dB.
It's a great answer, but I'm not sure I agree with the interpretation of the question.
Oh, okay.
We will repair to the bar, perhaps, on that.
That's where frozen comes in, right?
Right. Frozen margaritas, Dr. Schlossberg. We do have a question from online. Any recent developments regarding non-chemical batteries and capacitors? And so in general, I think this is a question about prime power and supporting that.
There have been some advances in batteries. The DoD and the U.S. government in general puts a lot of emphasis on battery research. I think everything that I've seen has been extremely incremental, no breakthroughs, but I'm waiting, and I think the community is eagerly waiting for breakthroughs, and that will only come after more investment, I think. Everything else has been very, very incremental.
And with that, I'm going to call our director up and hand over the microphone to the boss.
I'm not sure I do anything. I guess it's Edl, thank you very much.
Thank you.
It was
Appreciate
a
it.
pleasure.
Thank you for inviting me.
Thank you for coming. As a small token of our appreciation, we'd like to present you with a 60th anniversary AFOSR coin. This is to commemorate the 60th anniversary.
Excellent.
We hand them out to all speakers, and we're
I
really
appreciate
you
it.
coming.
Thank you. Thank you very much.
Thank you very much.
I'm honored.